Hi all, hope you are seeing the screen. Today I'm talking about the rotational matrix and its transformation. So this is a basic thing. Once you know about this one, then you can deduce for the homogeneous transformation. To start with, actually, let us try to understand the basics of the vectors. A vector is a quantity which has both magnitude and direction. A quantity which is just a magnitude, for example, distance is equal to 10 kilometers, does not have direction. It's a scalar quantity. A rocket launching from one position, that is from the launching pad, towards certain planet, that is going with certain angle, so which has its direction. So the velocity is a vector. So this vector identifies from which position to which point it is going. So it is basically determine the position of the point relative to the one reference frame or reference point or something like that. How do we describe this in the mathematical notations? Let us say I have two vectors x and y. The resultant vector of this x and y is, let's say, v or whatever, and magnitude is nothing but this the length of this arrow. Okay, and the angle determines the direction of this particular vector. Now, this vector has coordinates on x and y axis. That's why the p x y. I'll designate this particular point p as p x comma y. X comma y has some value quantity. That means the magnitude quantity is nothing but y. There is 5 on the x-axis and the 5 units on the y-axis. I will represent the point p as 5 comma 5. We'll go to the next one. Linear combination of vectors. I have a vector v. I can increase or decrease this vector by multiplying with some number. Let us say I'll multiply it by 5 or 2. I'm going to increase the magnitude of this vector, but the direction is not changed. I'm just trying to increase the magnitude when you multiply it. Next one, similarly, I can decrease the magnitude of the vector v, just multiply it by zero point 0.5 or half. So that means, in general, if a vector is multiplied with certain variable, let us say c, I can increase or decrease. That's where we got the actual magnitude of the vector. Now, with this basic notation, let's have a vector AV with certain magnitude A, another one BU. I don't know what is the magnitude, it's just BU. It's some certain random number, BU. What would be the resultant vector? So the resultant vector can be identified with one of the linear combination vectors principles that take this AV, put it at this head. It becomes like a parallel piped diagram or parallel piped theory. So based on this, we can say that the resultant vector is nothing but this origin to this particular point, sorry, origin to this particular point P. So the resultant vector is nothing but the addition of this vector plus this vector. That is nothing but AV plus BU. Remember this point. Now let us try to represent the orientation. What's the orientation? Why it is needed? In case of, let us say, robotic, gripper, it's not just the position which determines. I've spoken many times that orientation is important to describe, to hold that properly. Orientation is very, very important, not just the position, right? Or the interest of the object, certain orientation. So we have to have a definition of orientation, not just the position. I gave you an example of the a car position is fixed, but my robotic arm and its painting tool at the hand gripper has to rotate exactly to its position or orient itself to exactly paint at certain locations of the car. Car cannot move or P is fixed form, right? So orientation is very important. Now, in a three-dimensional axis, how do we represent the orientation? Let's try to understand the orientation. So I have a vector, let us say xb, yb, and zb, which has its some components u, v, and w. So the resultant vector from all these vectors, principal coordinates, is nothing but this is the point P. The point P is nothing but referencing to the frame B, which has its axis UXB, VYB, and WZB. Okay, the P has got the coordinates UVW. So from the previous example, I can write the resultant vector is nothing but the UXB, VYB, and WZB. That's the magnitude of the position P, or the magnitude of the resultant vector. Now, we know what is the coordinates of this frame B, which has XB, YB, and ZB is nothing but UVW in general, but preferably it's nothing but P is equal to UXB, VYB, and WZB. What is our next step? Our next step is basically to represent the um, the PB in terms of some other reference frame. I don't know what is the reference frame. This is frame A. Currently, this frame is B. I want to represent B in terms of A. That becomes the AP. That's what we want to identify. Before we go into that, I think we need to understand a dot product. It's a concept of dot product. What is a dot product? Let us say two coordinates, X and Y. There are two coordinates. So if I say there are two coordinate vectors, so there are two vectors x and y whose dot product is given by multiplying the magnitude of one vector by the magnitude of a second vector's projection on the first vector. What do you mean by that? The dot products, let us say these two coordinates, right? X dot y. I'm going to let's just say multiply the magnitude of one vector. What is the one vector? Let us say y by the magnitude of the second vector's projection on the first vector. That means I'm projecting this OA onto the vector y this way. I'm putting a torch over here. The shadow which lies here is called as the projection of the OA of this x vector onto the y vector. So this, what is this side? Adjacent side. So this can be written as, so cos theta is equal to what? Adjacent by hypotenuse. What is hypotenuse? Is mod x is the magnitude of this hypotenuse is mod x. So this is nothing but equal to x cos theta, right? Just hold on this thought x cos theta. So what is the x dot y is nothing but equal to x dot y, or the projection of x onto y is nothing but the dot products. How did you derive here? So x dot y is nothing but equal to x. The x is nothing but equal to the magnitude of the x. Y magnitude is nothing but equal to, you can also represent here the y magnitude is, y magnitude is x cos theta, and this y magnitude. Now, x cos theta is nothing but your projection. So projection is nothing but your dot matrix. Projection of this OA onto this particular onto this particular y vector. That gives a product matrix, the product of x and y. So I hope you know this now. So let us try to use this principle in the next slide. Now I have a solid rigid body called S here, whose associated coordinate systems or coordinate principal axis is x1, y1, and z1. Now, if I want to have the rotational transformations, we need to attach to the reference frame called x naught, y naught, and z naught. No, always note that the body origin point O and the reference origin point O remains the same. They're coincided here. Now I'll remove this body. I just keep the coordinates, vectors, and lines. Now, this gives the visualization orientation. What is the frame B now? Represented by the three principal axes, XB, YB, ZB. Frame A, represented by the XA, XA, YA, and ZA. Let's go move on. Now, the point P, position vector associated with the frame XB, YB, and ZB. I call this as point P associated with the frame B. Its coordinates is, just look at the magnitude of these vectors x, y, b, and zb, uxb, vyb, and wzb. You can see here. So the resultant vector is nothing but uxb plus vyb and wzb. In other words, the point P coordinate is UVW. So UVW, I'm not going to take UVW in this fashion. Normally, soon as any variable comes in, we'll put it like this. But I don't want to make it up because I want to have future multiplication. You need to, in order to have the future multiplication, I need to have one vector in row vector, another row column. One matrix should be in row, another matrix should be in column. Then only I can able to multiply. So I'll take this, I put the UVW in the transpose, UVW transpose. If you put a column into a row, that becomes a transpose. That's it. Okay. So next one. Okay. The PB is nothing but this transpose UVW that definitely satisfies this equation. The resultant vector is nothing but equal to UXB, VYB, and WZB. Okay. So now what we have to write? We want to transform. What do you mean by transform? Same P, which is referencing to XB, YB, ZB after reference to the frame A. Instead of frame B, I'm going to reference to the frame A. With reference to frame A, so I need to define the point P. So I call it as a point P with reference to the frame A. How do I do that? Put this point P, project it here onto the XA. That will become a dot matrix. The P and as well as YA. I'm going to show it on the y-axis because that's convenient to show. That's it. Okay. The same thing for all other coordinate axes. Just remember here, the when I try to put a project it, when I try to project this x vector that is nothing but OA onto the, let me just erase all these things. Why? Too much. Okay. When I try to project this OX onto the vector y, according to this definition, that becomes a dot x dot y. That becomes a dot product. Okay. The similar way, I'm going to use this p point p. I'm going to project it onto the ya. That becomes pb dot ya. Similarly, I can do it for the xa. Similarly, I can do it for the za. Any questions so far? Just note it down and just please ask me. The same thing I have written here. Now we know what is pb. Pb is what? This is the formula. Put it over here. UXB plus VYB WZB dot XA. XA. I represented this one. I'm going to represent here. A similar way I'm going to represent here. All three are done. Now, the dot matrix you can multiply in the similar fashion that we have. U, XB, XA, V, YB, XA. Just you're trying to multiply all these things and you get this particular one. Now, I just want to show you like how the matrix works. When you have two variables, one you can put it in the in the row column. You can retain this XB. You can retain this XB, XBYA, XBZA as a column here. Okay, YBXA, all these columns you just make it here, resume or retain it here, retain here all the columns. Another variable UVW, okay, the UVW, I put it in the another matrix. This is how actually. So if you try to multiply with this one, and you will get back to this the same one. Okay. So the entire thing is nothing but a 3 cross 3 matrix. I can represent it using the A or B. Rotational matrix of the frame B with respect to the frame A. UVW is what? Is your coordinate system here. That is nothing but your vector point PB. Either you call it as this one, that is the BP. Now, with respect to this, the point P with respect to the A is nothing but the rotation matrix multiplied by the the position which is associated with the frame B. Now, what it does, the AP is nothing but the same point. It is not a different point. AP is the same point. Earlier, this point was referenced with respect to the B coordinates or the B frame. Now the P is referencing to the A frame. That's it. That's what it transformed from B frame to the A frame. That's it. That's the whole entire rotational transformation. You can read this definition here. It changes the description of um, vector BP, which describes a point in space related to the frame B, into AP, which is a description of the same point but expressed related to the frame A. That's what I said. Earlier, P was associated with the frame B. Now P is associated with frame A. Frame A means all XA, YA, and ZA. Okay, this is the rotational transformation. Now we know what is ARB. This is the rotational matrix to represent the orientation. This is nothing but your coordinates of the point related to the frame B, coordinates of the point P related to the frame B. When you multiply it together, this will the position point P expressed related to the frame A. This is nothing but transformation. Now, rotation transformation, we get it. We mapped it now from one frame to another. The next one was, what was the next one? I think the homogeneous transformation. What is a homogeneous transformation? This is the base frame, XA, similarly YA and ZA. From here, there's a point. Again, this is something YA and ZA and so on and so forth, right? This particular stuff, actually, I can represent whole thing in the rotational form, in the rotational matrix form. If I want to have a rotational matrix form, as I told, I have to put this always, imagine this particular brick, okay? I want to put this brick in another known frame, all right? The same thing, I'm writing it here, another known frame. But what is the difference is the only thing is that here, when I represent it, there is no offset between the base frame to the rotating frame. That is frame B. But here, you have an offset here. This offset is called, let us say, this is a vector which is specifying to the B origin. This is vector with respect to the A. This is B frame. Of course, this is A frame. Now I want to represent this, have the reference vector, merge it here, coincide it here, and ensure that this imagination or the coincide vectors or imaginary vector coordinates are in parallel to this particular base vector. Based on this is nothing but your rotational matrix. This is displaced from origin point 0 to here. So I can have this one. This is A, P, V, O, or G plus this rotational matrix identified by putting the imaginary coordinate axis and everything. This it's nothing but a homogeneous transformation of the frames. Okay. I hope this is clear. If you have any doubts, please do note a point and just let me know. Okay. Thank you all.